Welcome to lecture number 17. This lecture, we are going to continue our discussion on the substitution and elimination reactions. Specifically, this lecture looks at E2 elimination. Okay, so this is bimolecular elimination. Okay, so just an overview of the general reaction. What we're considering with an E2 reaction is some sort of carbon system that contains an X group here, which is some sort of leaving group, okay? The leaving group is going to be on both substitution and elimination reactions. And for elimination reactions, we are also going to have a hydrogen in red here at the beta position, okay? So if we remember alpha and beta, let's take green here. If we're referring to this leaving group, the alpha position is the carbon next door, and the beta position is the next carbon down the chain. So for an elimination reaction, for an E2 reaction, we need a leaving group, and then we need a hydrogen on the beta carbon, okay? If we have both of those things, then we can have an E2 elimination. What happens in this reaction is we get the leaving group, X in this case, and hydrogen both leave the molecule, and what's left over is a double bond, okay? So we left over with a double bond. The base takes the hydrogen, and then we're left with X minus. So how does this look? Let's start here at our base. We'll go through a mechanism. Okay, this is a concerted mechanism, meaning this all happens in one step. The first step here, we are going to take our base, starting with the lone pair on the base, and the base is going to take the hydrogen. Okay, the base takes the hydrogen. The hydrogen's electrons in this CH bond, they're going to be left behind, okay, just like we've seen on other proton reactions. We're just taking this proton, leaving the electrons behind. But instead of leaving the electrons behind on the carbon, what we're going to do is we're going to leave the electrons behind as a double bond. They actually drop down right in between the two carbons, and these two electrons are left as a double bond. Okay, so the two electrons drop right down in between the carbons here, make a double bond, and in the same step, the leaving group is expelled with its electrons, because this carbon over here on the left that I just circled, this carbon can't have 10 electrons. So if 2 electrons come in to make this CC double bond, that means 2 electrons must go out, okay? So you can almost think of these 2 electrons in this CH bond. When these 2 electrons come down and form this double bond, that sort of kicks off, that process kicks off the leaving group with its electrons in order to make space for that CC double bond to form, okay? So again, just looking at the mechanism here, the base grabs the proton transfer, we know this step. The electrons in the CH bond here drop down to form a pi bond between the two carbons, and the leaving group is kicked off with its electrons, okay? So we're left with X minus, okay? That leaving group still has its electrons, okay? So that's the mechanism for an E2 reaction. Relatively simple, relatively straightforward, although there are a few minutiae that we will discuss. Just in terms of nomenclature, this can be called a beta elimination, a 1,2 elimination, simply an elimination, or if the X, our leaving group, is a halogen, we could call it a dehydrohalogenation, because we're removing both a hydrogen and a halogen. Okay, so these are the words you may see for an E2 reaction. And finally, why do we call it E2? Well, just like the SN2 in the rate equation, the rate determining step has two parts to it. It's dependent on both the concentration of the alkyl halide as well as the base. So we take the basic rate equation, which is rate equals K, and we multiply it by the concentration of the alkyl halide and the concentration of the base. These are both first order, okay? Meaning that if you double the concentration of either one, you would double the rate of the reaction. So that's the general overview of E2. Okay, so let's first discuss a little bit about double bonds. We need to know a few things about double bonds, and then we will look at some of the details for the E2 reaction. Okay, so now looking at double bonds, just a little bit of information on double bonds before we start. For nomenclature, it's just as with single bonds. The only real difference here is that we need to make sure we include the double bond in the parent chain and give it the lowest possible number. And we ignore the other groups on the chain and just focus on that double bond and give that double bond the lowest possible number. Okay, so if we look at a molecule like this on the right, if we wanted to name this, first find the parent chain, make sure the double bond is in the parent chain. So I think we go right across from left to right here. 1, 2, 3, 4, 5, 6, 7. So we have a heptane parent chain. We have a double bond, so heptane becomes heptene. Heptene. And we would call this 2-heptene since the double bond starts on the second carbon. 1, 2, 3. So we would call this 2-heptene, okay? Not 3-heptene, 2-heptene. You give it the lowest number possible, and we hit the double bond on the second carbon, okay? So 1,2-heptene, that's the parent chain. Then we need to look at the other groups we have. 4, 5, 6, 7. We have a methyl group on carbon 6, right? So we have 6-methyl, and we also have 5-methyl, and we have 5-methyl. We have 2 methyl groups on the 5th carbon. We have a methyl group on the 6th carbon. So altogether, we would have 5, 5, 6. Trimethyl 2-heptene. Okay, so that would be how you name double bonds. Very simple, very similar to the alkanes. Just make sure you include that double bond in the parent chain. Give it the lowest possible number. Okay, so that's nomenclature of double bonds. What about stability? So this is one thing we should be aware of for the next topic we talk about. Double bonds are more stable when they are more substituted. So we would call these bonds I've drawn down on the bottom mono-substituted, di-substituted, tri-substituted, and tetra-substituted. So if we have a double bond with 4 different things attached to it, that's as many things as we can attach to it as possible, right? Because a C-C double bond means we have 4 spots left over. So 1, 2, 3, 4. So tetra-substituted is the most substitution we can have. Obviously, mono-substituted is the least amount of substitution we could have. You could also just have ethylene, C double bond C, with just hydrogens, right? That would be the most basic olefin you could have. But nevertheless, going from mono-substituted up to tetra-substituted, the more substituted you are, the more stable you are. And the reason for this stability, the increasing stability as we increase substitution, is because of hyperconjugation, very similar to the carbocation stability, okay? Now, looking at the dye substitution, we could have either a cis or a trans configuration. The dye substituted olefin with a cis configuration means they're both on the same face, and the trans configuration means they're on opposite faces. Okay. And now the trans substituted double bond, the dye substituted double bond that's trans, will be a little bit more stable. Of course, when we have groups that are more spread out, that is sterically favored. Okay. So trans is a little bit more favored than cis. And obviously, as we increase the substitution, we also increase the stability. Okay. Okay, so now hopping into some more details for the E2 reaction, let's look at this substrate. We have this bromine here. This is our leaving group. And we have a 1, 2, 3, 4, 5 carbon substrate. This bromine is attached to this carbon here. This carbon we would call the alpha carbon. Okay, that's what the bromine is attached to. And then we have several different beta carbons. We have this beta carbon out here on the end of the chain. And we also have this beta carbon over here on the right, which is inside this chain here. Let's distinguish these. Now these both have hydrogens. Let's call this one a red hydrogen out here. And we'll call this beta carbon with a blue hydrogen. We'll label it with a blue hydrogen. Now, some of you may see this carbon back here, this beta carbon. Just be aware that this beta carbon in the back is chemically equivalent to this beta carbon, the two that I circled. Okay, and if you don't see why that is, you might want to build a model or pause and think about that. But ultimately, these two beta carbons are exactly the same. Okay, so it doesn't matter which one we pick. I'm just picking this one right down here. But ultimately, it doesn't matter which one. If we get elimination to occur on either of these, then we would have exactly the same molecule. Okay. So I'm just picking this beta carbon right out here. We'll call this the red one. And we'll call this one over here on the right the blue one. So we have two different beta carbons that we could perform this E2 reaction on. And again, the mechanism for this E2, we're going to abstract a hydrogen. And then we are going to bring down, we'll continue the mechanism just with this blue one here, bring down the electrons to form the double bond, and we'll kick off that leaving group. Okay. So that would be the mechanism for that one. I'll erase the red arrow here just for clarity. So if we follow these arrows, if we take the base, we abstract the proton, we bring down the electrons to form a double bond, and we kick off that leaving group with its electrons, that would put a double bond at this position here. So I'm going to circle in blue the product we would get from that reaction. Okay. Now, if we were to abstract the red hydrogen, we would end up with this product circled in red. So we have two different products, and these products arise out of differences in regiochemistry. And when you see the word regiochemistry, all you need to do is ask yourself, where is the chemistry occurring? That's all regiochemistry means. It means on what part of the molecule is the chemistry occurring. So we have a regiochemical discrepancy here where we could have the reaction either take place on the blue hydrogen or the red hydrogen. We have two different possible sites of reaction. So we have a regiochemical consideration to make. Where's the chemistry going to occur? Will we get elimination on the blue hydrogen, or will we get elimination on the red hydrogen? Most often, there's competition between the two, and it's very rare that you only get reaction at one site when there are potential sites for reaction. This is a big study in chemistry, in organic chemistry, in synthetic organic chemistry especially. We want to be able to make very precise and specific bonds, but it can be very difficult when there are a lot of different sites that could react. Okay, so most often you'll get a mixture of the two. However, we can sort of fine tune which one we prefer based on the reagents that we select. I'm going to clean this up a little bit. Let's erase that mechanism for now. And let's talk about these two products. So the red product, if we eliminated this hydrogen over here on the red hydrogen on this beta carbon, we would call this the Hofmann product because we end up with the double bond that is less substituted. Okay, so the Hofmann product is the double bond that we get that is less substituted. And the Zaitsev product, quite obviously, is the more substituted double bond that we end up with. In this case, the blue product. So the blue, this is the Zaitsev product, and the red, this is the Hofmann product. Okay, we see that the red double bond is only di-substituted. Okay, let me circle those two branches. We have this branch out here, and we have this branch out here, di-substituted. And the blue carbon is tri-substituted. We have 3 different groups coming off that double bond. So that blue double bond is going to be our Zaitsev product. Okay, so let's consider these with different bases. I have started this little chart here, and let's fill this out. If we were to use a small base like ethoxide, ETO minus, an ethyl group with O minus, we would end up getting about 71% of the Zaitsev product and about 29% of the Hofmann product. If we increase the steric bulk of the base, we would end up with about 28% Zaitsev and about 72% Hofmann. And if we increase the steric bulk even more, then we increase the discrepancy and we go to about a 92% Hofmann and 8% Zaitsev. So looking at this chart here, we can make a conclusion and we can draw a trend. What's the trend that we can make looking at this chart? As we increase the size or the steric bulk of our base, we increase the formation of the Hofmann product. So bulkier bases favor the formation of the Hofmann product, and this is due to sterics. Okay, this is due to sterics. Let's consider that. I'm going to draw up here the base, O minus T-butoxide, a bulky base. Now, which of these 2 hydrogens is this bulky base going to grab? Now, I like to think about this as the base here, this bulky base being a person, and it's going up to a fruit tree, think of an apple tree, and it's going to pick an apple. Now it could either pick this red apple or this blue apple, but most likely this person is going to come out and just pick this red apple. Why? Because it's hanging out far away from the branch. It's sticking out in space. There's not a lot of steric hindrance around it. This blue apple, on the other hand, is much more protected. It has all of these different groups around it. It has a CH3 over here. It has this big part of the molecule over here. This blue hydrogen is much more protected. You can think about it as an apple that's very far in the tree. This large, bulky person, this base, is going to be less likely to reach in and grab that apple that's much more buried. Okay, this red hydrogen is just a low-hanging fruit sticking out in free space. It's much easier for a large, bulky base to simply grab this red hydrogen than it would be to grab this blue hydrogen. Now, if you pick a small base, if you pick something like ETO minus or just OH minus, a small base like a small child, is going to be able to jump right up into the tree and grab any fruit that it wants, right? A small child isn't going to worry about which fruit's the easiest to grab. They're going to climb up in there and they can grab any fruit they want, okay? That's how I think about it. Makes it easier for me to remember. Ultimately, you should just be aware of the trend that a large, bulky base is going to favor formation of the Hofmann product because it just wants to grab those hydrogens that are less sterically hindered or sticking out in free space. Okay, so those hydrogens on the very ends of the molecule. Okay, so some bulky bases that you may see. Some bulky bases you may see, obviously the T-butoxide. This is the most classic example. This could be paired with a sodium or potassium counterion. And you may see it written out as T-butoxide O, and then either K or Na, so T-butyl OK or T-butyl ONA. This is the most common example you'll see, sodium or potassium T-butoxide. You could also see diisopropylamine. This is a nitrogen with two isopropyl groups, okay? Diisopropylamine, or you could see LDA, which is the exact same thing, but deprotonated. So you have a lithium counterion there. This is LDA, lithium diisopropylamide. So these are all bulky bases that you may see, LDA, DIPA, or T-butyl O, Na, or K. The T-butoxide is going to be the most common one you see. And if you have to provide a bulky base on a test, for example, this is the classic go-to one, okay? There's hundreds, and they're varying in bulk, so it's not worth memorizing them. Just understand the basic trend that as you increase the bulk of the base, you increase the formation of that Hofmann product because that bulky base just wants to grab those hydrogens on the ancillary parts of the molecule, okay? So now our final consideration for the E2 reaction is going to be thinking about whether we end up with a cis or a trans double bond where applicable, okay? Sometimes it won't be a question, sometimes it will be. So this is going to be the stereoselectivity question, stereoselectivity. And what we're doing, what we're asking when we consider stereoselectivity is we're asking on what face of the molecule is the chemistry occurring. Regiochemistry, right? That's asking where is the chemistry occurring. Stereochemistry is asking on what face of the molecule is the chemistry occurring. So in this reaction, we have two hydrogens here. There's one in red and there's one in blue, and it could be on the other face. I'm just picking this side. It could be on the other side over here on this blue carbon. I'm just picking this one on the right. So we could get elimination of either the red hydrogen or the blue hydrogen. Eliminating one would give us the trans double bond. Eliminating the other would give us the cis double bond. Now the major product of this reaction is going to be the trans double bond. And usually it is the case when you could form either the trans or the cis, typically the trans double bond is favored. The trans double bond is typically favored because it's a more stable product and it has a more stable transition state as well. So it's more stable and it's easier to make. Now this isn't always the case. Sometimes the cis product will be favored or have a more stable transition state, and you can manipulate your reagents and substrate to form a cis double bond. But typically speaking, the major product will be the trans double bond. Now, where this really comes into play is when you have stereocenters or potentially a ring system, which we'll see in the workshop. So for the last little bit of class, I want to look at this substrate down here in this box, and let's consider the stereochemistry for E2 elimination using this substrate. So we have this substrate here with stereochemistry defined. We have these hashes and wedges. We have our leaving group here, bromine, and we have only one beta hydrogen, which is this one over here. All of the other beta carbons have no hydrogens, right? So if we consider, for example, let me draw the T-butyl group out, just so you remember, the T-butyl group is 3 carbons connected to the same carbon, 1, 2, 3. So this would be the only other beta carbon in red here. And that doesn't have any hydrogens on it. Okay, so we only have one beta hydrogen. So there's only one hydrogen that we could eliminate for E2 reaction. Okay, so let's look at this in more detail. When we do E2 elimination, we require coplanar, leaving group, and hydrogen. This is very important. Okay, E2 reaction requires coplanar, leaving group, and hydrogen. So that means when we have a hydrogen and a leaving group, we want them to be in the same plane as each other. And the best way that we can look at that is with Newman projections. So hopefully we remember Newman projections. I'm going to draw a Newman projection of this molecule looking down this CC bond right here in the middle. Okay, so the Newman projection for this molecule, we would have a methyl group coming out to the left, a phenyl group coming out to the right, and we would have a hydrogen going straight down. On the back carbon, the bromine, we want to be straight up, which it already is, which is good. The T-butyl group is over here. T-butyl group is there, and then we have this hydrogen. Okay, so I'm just looking down that CC bond on this red arrow here, and I'm drawing a Newman projection from that perspective. This methyl group is out to the left, the phenyl group here is up to the right, etc. Okay, so there's the Newman projection. Now, when we do an E2 elimination, when we take a base and grab this beta hydrogen, do the elimination, and kick off the leaving group, we want coplanar leaving group and hydrogen. Let me highlight these with blue. We have this blue hydrogen here, and we have this blue leaving group here. We have this blue hydrogen here, and we have this blue leaving group here. So these are coplanar because they're in the same plane. Okay, they're in the exact same plane. Now, specifically, this is anti-coplanar, right? They're in the anti position. And this is ideal, remember, because the anti configuration is favored to the cis, to the syn configuration. We also call it anti-periplanar, anti-coplanar, or anti-periplanar. You may see either one. But this is the configuration that is required when we do E2 elimination. We need these to be coplanar. It's possible for them to be syn coplanar and have the bromine and the hydrogen overlapping each other. But most commonly, you'll see this anti-configuration, this anti-periplanar configuration, where they are in the same plane, but anti to each other. Okay. So when we get the E2 reaction to occur, we have a base, grabs the hydrogen when they're anti-periplanar. The electrons come down and form a double bond between the 2 carbons that we're looking down, and the bromine is kicked off. That means we're left with a double bond between the 2 carbons that we're looking at. I'm going to bold the center of the circle here. We're looking down 2 carbons. They're right on top of each other. there's now a double bond between those, and the bromine and the hydrogen are gone. So what would that look like? Well, we'd have a double bond. On the front carbon, we have a methyl group and a phenyl group. And on the back carbon, we have a T-butyl group and we have a hydrogen. So this is the only product that we would form via E2 elimination, starting with this substrate on the left. If we started with this substrate on the left, the only product that we would form is this double bond on the right, okay? And the reason for that is because E2 elimination requires the leaving group and the hydrogen to be coplanar, okay? Coplanar. So almost every single time they will be anti-periplanar. They will line up opposite each other in the same plane, and then the E2 reaction occurs. Okay. If this last part didn't make much sense, we're going to get more practice in the workshop. This is the tricky part for E2. But at the end of the day, just remember this for now. Just remember that E2 elimination requires the leaving group and the hydrogen to be lined up in the same plane. Okay, remember that for now, and we'll do some more practice problems with it. Okay. Okay, that's everything for lecture 17. Next lecture, we will look at the SN1 and the E1 reactions. Those are two different types of substitution and elimination. And then we will do a nice lengthy workshop and review on all the substitution and elimination reactions because they're very important.